today we are going to kind of finish the topic of simplex algorithm, our first iteration of learning simplex algorithm. Next week we'll talk about quite a different topic. It's called duality. It's very interesting. It involves a little bit less calculations, more interesting stuff. But today we'll have to learn another method basically of writing how to perform the simplex method. And it's somewhat akin to what you did in linear algebra. You first wrote down all the equations explicitly, and you subtracted one from the other and try to make the additions. Later you omitted the names of the variable and you just had a matrix of coefficients, matrix of coefficients on the right, and you performed Gaussian elimination. So that's what we are going to learn today. How to write all the computation in such a way that we don't have the names of the variables. So we'll start with an example, simple one, and we'll do it pretty slowly. So what we're going to do is write a Tableau, and you'll see what it is. So basically, our first example will be quite a typical problem: maximize 4x1 plus x2 plus x3, subject to the following constraints: 2x1 plus x2 plus 2x3 smaller or equal than 4, and 2x1 plus x3 is smaller or equal than 4 as well. So that's the problem. What do we do usually as a first step in solving such a problem? So what is the first step in solving such a problem?
Slack variables.
Introduce the slack variables, yes. So let me now introduce them, but in slightly different manner. Usually we write them as a dictionary. We say that the first slack variable is the difference between 4 and this. As well, I can say that the first slack variable is a number which I have to add to the left side to get the right side. So I introduce the slack variables in such a way. So my constraints, I will write them in such a way: 2x1 plus x2 plus 2x3 and plus a new slack variable x4 is equal to 4. So if this is smaller than that, I can add something positive and make it equal. Similarly, here I will introduce the slack variable x5. And what I want is just x1 to x5 to be positive. So for now I didn't do, I did more or less nothing. I just introduced the step variables. It's exactly what we do usually. x4, if you think, it is the difference between 4 and this expression. Okay, also we can give a name to our objective function. Our objective function is for x1 plus x2 plus x3, and it is our objective function. Okay. Now here I don't have any inequalities. Here I have usual equations, like you have in linear algebra. What do you do when you want to solve equations in linear algebra? Well, you don't perform all the steps using the names of the variables, you just write the matrix of coefficients. Here it's called a table. It looks like this. I'll just record the coefficients. 2, 1, 2, 1, 0, 4. Second row. 2, 0, so nothing with x2. 1, 0, 1, 4. So once again, nothing with x4 and 1 times x5. And finally, the last one, x4, 1, 1, nothing with x4, nothing with x5. And now there is, well, there are some conventions what to write here. I'll use kind of non-standard convention, but I think it's pretty logical. I'll just write it. So z will be my objective function. It is literally equal to 4x1 plus 1x2 plus 1x3. And I'll separate this row because it's special. It's my objective function. I'm trying to maximize z. Okay, so I basically just recorded the same problem, well, without writing x1, x2, x3, x4, x5. That's all I did. Of course, you can reconstruct the original problem from this one, or you can reconstruct this table from the original problem. Well, do you see the basic variables? What are the basic variables? Yes, the basic ones. So what are the basic variables in the original problem? So it's the variables which we write as, usually we say a variable is some expression in terms of the non-basic ones. x4 and x5, exactly. So in the first step we set all the decision variables to 0, and these are the basic variables. x4 is 4 minus all the rest. Well, here are the basic variables right here. x4 is 4 minus the rest, and it's quite special in the sense that the whole column which corresponds to x4 is 1, 0, 0. Similarly, x5 is a basic variable. You see 0, 1, 0. So you can just look at this table and see the basic variables. 1, 0, 0, 0, 1, 0. These are the basic variables. Okay, let's try to perform a step of simplex algorithm. So usually what we are trying to do is choose a non-basic variable, try to increase it as much as you can, and make it basic. So which variable is it? x1, yes. So usually we take the variable with the largest coefficient. In this expression, it's obviously it's this one, x1, well, similarly, 4, 1, 1, the most positive largest coefficient is 4. So we'll take this variable, it will now become basic. Okay, which of the constraints will be the most strict constraint on this variable? Sorry? Oh, yes. So in this particular example, so what are the constraints? How much can I increase this x1? Well, if I keep those at 0, I can increase x1, well, 2 times x1 plus this variable must be equal to 4, and they must be both positive. So I can increase x1 such that 2 times x1 is still smaller than 4. So basically I can increase x1 to 4 divided by 2. Similarly from here, I can increase x1, well, up to 4 divided by 2. So here I have kind of type. Well, let me resolve it by the small subscript rule. I see that the top row is, I'll just choose the top row. Or maybe, okay, yes, let's choose the top row. Okay, next, I'll try to make this variable basic. What does it mean? Well, usually we could have thought about, let's try to express one in terms of the others. Here, being the basic variable means just you have a column like this, 1, 0, 0. So let's make this column 1, 0, 0. How can we do this? Well, first by Gaussian elimination. You will divide this row by 2. You will subtract, well, 1 times this row from here, and 2 times this row from here. So let's do this. So So once again, my goal is to make the first column 1, 0, 0. Why is it my goal? Well, exactly because that corresponds to having a basic variable. How can I achieve this? Well, I'll divide the first row by 2. I will subtract from the second row 1 times the first one. And I'll subtract 2 times the first row from the last row. So 4, 1 minus 2 times 1 minus 1, 1 minus 2 times 2 minus 3, 0 minus 2 times 1 minus 2, 0 minus 2 times 0, 0, z minus 2 times 4, z minus 8. So this is my second Tableau. Sorry, I'll just check if my camera is on. I think that it is actually on.
It is on.
I usually see no, this on. Okay. Sorry about this. Okay, so here's my second Tableau. If you wish, you can, if you're not quite sure that this is what you wanted to do, well, you can always rewrite this in the form of dictionary. You can say that here you have x1 is equal to 2 minus 1/2 times x2 minus 1 times x2, x3 minus half times x4. So you see that this dictionary x1 appears on the left, all these variables appear on the right, and similarly here, x5 is equal to 0 minus, well, the sum of those. Okay, what about, so here we have our basic variables, x1 and x5. So maybe I'll write this, x1, x5, and our basic. Did we succeed in improving our z? The value of z here was, once you set the non-basic variables to 0, which means these variables to 0, you get z which is 0. What happens here? Once you set the non-basic variables to 0, you get z minus 8 being 0. So z is 8. So here z is equal to 8. And is this optimal? Yes. Why? Basically, this rule tells me z minus 8 is minus x2 minus 3 times x3 minus 2 times x4. So it is basically always negative because x2, x3, x4 are always positive and they come with negative coefficients. Well, z minus 8 is always negative, so z is at most 8 for any solution. So this is optimal. The only way to achieve this is to make these variables equal to 0, x2 is equal to 0, x3 is equal to 0, x4 is equal to 0. What about x1 and x5? Once again, you can read it directly from here. Once you set these variables to 0, x1 is equal to 2, and x5 is equal to 0. So basically you have, well, basically this method is as good, if not better, than the previous method of using the dictionary. In a way, it involves less manipulations going from kind of left side to right side, remembering which variable enters which is. Here we have, well, some rules which are quite easy to remember. So a basic variable corresponds to the column with all the zeros but one at one of the places. And well, once you want to make a pivot, just make a non-basic column like this into basic like this. By doing our simulation. have more examples of this, but any questions about this example? Yeah.
So, did you get the values of x1 and x5 by just plugging them into the equations?
So basically, I mean, if you want kind of rule to remember, they appear in the right column. If you want to understand where they come from, well, once you set the non-basic variables to 0, you see that the first row tells you x1 is equal to 2, the second row tells you x5 is equal to 0.
Okay, so you just plug them into the equations.
Yes. All right. Okay, other questions? Okay, so let's have some more examples, and I'll try to cover some examples which involve situations which, well, we might not have seen previously. So the next example will be like this. Maximize 3x1 plus 3x2 plus x3 subject to x1 minus x2 plus x3 smaller or equal to 2, x1 plus x2 plus x3 smaller or equal to 2, and 2x1 plus x2 plus 4x3 smaller or equal to 5. So, and of course, x1, x2, x4, x3. Okay, so once again, it is a problem. Once we plug in 0, 0, 0, we get a feasible solution. The right hand side here are positive, so we don't have to apply the two-phase simplex method. We can start with the feasible solution 0, 0, 0, introduce the step variables. So now we know how to introduce select variables directly into the Tableau. We'll just copy the matrix of coefficients here. 1, minus 1, 1, 1, 1, 1, and 2, 1, 4. Besides it, we'll write the identity matrix. 1, 1, 1, all the rest zeros. So this is the select variables. I added x4 to the first row, x5 to the second one, and x6 to the third one. On the right side, I have 2, 2, and 5. And my objective function, z, is 3, 3, 1, and all the rest zeros. So that's my first table. Once again, what I did is just introduce the select variables. They're right here. I kind of joined an identity matrix to my original matrix from the right. That's what it amounts to. In other words, I just added x4 to here, x5 to here, x6 to here. Okay. Let's go first pivot. Which variable will I try to increase? Which variable will become basic in the next step? Well, yes, I have a choice. x1 and x2, they both come with the largest coefficient 3 in this row. And, well, let's use, I don't really have, actually we might have some reference. Depending on how much the z will increase if you try to increase one or the other. Actually, maybe it's a good idea to think a little bit whether one of them is better than the other. If I try to increase x1, how much will I be able to increase it? Two, yes, so the first row tells me increase it at most up to 2, basically 2 divided by 1. Second row tells me increase it at most up to 2 divided by 1. Third row tells me increase it at most up to 5 divided by 2. So the strictest one is 2 divided by 1, 2. And similarly, what happens for the second variable? How much will it increase? Well, yes, true as well. What does the first row tell me about it? Nothing, right? So in the first row, I have something like this: x4 minus x2 is equal to 2. Once I set these variables to 0, x1, x3, x4, x1, x3. So basically here, I can increase x2 as much as I can. Correspondingly, x4 will increase, and nothing will become negative. So first row doesn't tell me anything. Second row tells me you can increase x2 at most up to 2, and third row tells me you can increase x2 at most up to 5 divided by 1, 5. So even in this way, I still have a type. Both variables will increase up to 2. Well, let me choose this one. Let me make an arbitrary choice, or small subscript rule, whatever. Okay, we already, so this is called the pivot column. The column which we'll try to make basic. The pivot row, the row which imposes the strictest inequality about my variable, well, we just discussed it. This imposes an inequality of 2 over 1, 2 over 1, and 5 over 2. So basically, you can read this, which one is largest, by just taking this divided by this divided by this, and this divided by this. Strictest one of those is the first and the second. Well, once again, it doesn't matter which one I choose. Let me choose the first one. Okay, now let's do the pivoting. I'll try to make this whole column into 1, 0, 0, 0. By doing, of course, Gaussian elimination, I'll leave the first column, the first row as it is. It already has a 1 here. I'll subtract the first row from the second one. 0, 1 minus 1, 2, 0, 0, 1, 0, 0. Okay, I'll subtract 2 times the first row from the third one. 0, 1 minus 2 times minus 1, 3. 2 minus 2. 0, 0, no, 0, 1. 1. Yeah.
In the second row, shouldn't it be 0, 2, 0, negative 1?
0, negative 1, yes, maybe. So this should be negative 1. 1, 0, 0, yeah, thank you. And finally z, my objective function. I'll try to make this 0. I'll subtract 3 times the first row. 0, 3 minus 3 times the first row, 6. 1 minus 3 minus 2. 0 minus 3 minus 3. 0, 0. And here z minus 2 times 3, 6. So you see that in this pivoting, I increase the value of z up to 6. Now my basic variables are x1, x2, x1, 2, 3, 4, x5, x6. And I still can increase z. How do I see this? Well, I look at the last row. I look for any positive coefficient. In fact, I'm looking for the one with the largest positive coefficient. Well, here it is. 6 is the only positive coefficient. I can try to increase x2. So we repeat this procedure. We choose this column as the pivot column. I will try to make it basic. Which of the rows will be the pivot row? Which one will impose the strictest inequality? So let's look. What about the first one? Right, no inequality at all. So here it is this minus this is equal to 2. You can increase this will increase as well, no problem. In other words, 2 divided by minus 1 is negative, so I don't even consider it. Okay, here the inequality is you can increase x2 up to what? 0. So basically you cannot increase x2. Okay, that's a little bit discouraging. The last one tells you can increase it up to 1 over 3, 1/3. Okay, so the strictest one is of course this one. Unfortunately, it tells you cannot increase x2 at all. Well, so we will not increase x2. We will not increase z, because basically we are not going to change any of the variables. But still we are going to do the pivoting. It is, well, how did we call it last time? We had some iterations which did not increase the value of z, did not change the values of the variables. Degenerate, yes. So here we have encountered a degenerate iteration. Okay, but still we can do the pivoting, no problem. We'll try to make this equal to 1, 0, 0, 0. That's the pivoting. Okay, so let's do this. I will add to the first row 1/2 of the second one to make this coefficient equal to 0. So it's 1, this will become 0, 1, 1 minus 1/2, 1/2, 0 plus 1/2, 1/2, 0, 2. That's my first row. Second one, I want to make this coefficient equal to 1. So divide everything by 2. Third row, well, I'll try to make this coefficient 0, so subtract 3/2 of the second row. So it will be 0, 0, this minus 3/2, 2, this minus 3/2, so minus 1/2, minus 3/2, 1, 1. And finally, what happens with z? Well, I'll subtract 3 times the second row to make this coefficient into 0. So 0, 0, minus 2, still minus 2, minus 3 times minus 1. So it's 0, 0 minus 3 times that, well, minus 3, 0 minus 0, and z minus 6, minus 3 times 0, still z minus 6. Okay, so that's my result of this pivoting. Can I continue? Okay, why not? Which row tells me that I cannot continue?
Coefficients are negative.
Yes, the last row, all the coefficients are negative. Minus 2 and minus 3, both negative. I cannot increase any of the variables to make that even larger. So even though I didn't change the value of z from this iteration to this one, that iteration left me some hope of increasing z eventually. This iteration tells me, no, now you're done. We have the optimal solution. Okay. So here we encounter the degenerate iteration whose only kind of output was telling us, well, now you're done. After you finish this degenerate iteration, yes, you didn't change anything, but now you are sure that you will never change anything. You already achieved the optimum. Okay, what are the variables which will give me z equal to 6? What values for the variables will give me z equal to 6? So typically we look at the non-basic variables, which are in this example x3, x4, x5. and we set them to 0. And we adjust the basic variables accordingly. That's what we typically do. Well, that's not exactly what we have to do here. Look at the last row. Z minus 6 is minus 2 times x3 minus 3 times x5. If you want z to be equal to 6, if you want to achieve the largest possible value, well, all you have to do is just set x3 equal to 0 and x5 equal to 0. So z is equal to 6 when x3 equal to 0, x5 equal to 0. What about the other non-basic variable, x4? x4 is also non-basic, but for some reason we don't have it equal to 0 here. So the reason is by coincidence, which happens sometimes. The coefficient here is 0. It didn't have to be 0. Here, the coefficient had to be 0 because it is the basic column. Here it has to be 0. Here it has to be 0. Here it is a coincidence that it is 0. Usually it would be some negative number. But in this particular situation it is 0. So basically z is equal to 6 can be achieved by setting these two variables to 0 and x4, well, it looks anything. Okay, so x4 will be a parameter. Okay, what will happen with x1, x2, and x6? x1 will be, you can read it from here, so you can completely ignore this column because x3 is equal to 0. You can completely ignore this column, but you cannot ignore this column because x4, well, is a parameter now. So x1 is 2 minus 1/2 of x4. x2 is 0 plus 1/2 of x4. x6 is 1 plus 1/2 times x4. Okay, so did I solve my problem completely now? So indeed, if I set x4 to be any number, x3 equal to 0, x5 equal to 0, and x1, x2, x6 equal to these expressions, all these constraints will be satisfied. This will indeed be equalities, and z will be equal to 6. Did I solve my problem? No. Why not?
x4 has to be within a range, so that x1 is not negative.
Okay, yes. So all the parameters have to be positive. So first of all, x4 should be positive. Also, x1 should be positive. So what it tells about x4 is that x4 is at most 2 divided by 1/2, 4. From x1 being positive. x2 should be positive. Well, it tells you once again x4 is positive. And x6 has to be positive. It tells you that x4 is greater than negative 2. Okay, so once all this happens, x3 is 0, x5 is 0, x4 is any parameter which satisfies these inequalities, and x1, x2, x6 are like this, we have a solution. So let's write down now the complete answer. So answer the answer should involve just the decision variables, and the answer is like this. x1 is equal to 2 minus 1/2 x4, x2 is is equal to 1/2 of x4, x3 is equal to 0, well, x4 is any number between 0 and 4. So this inequality is basically amount of x4 being from 0 to 4. And once this happens, z is equal to 6. So in this particular example, the solution set, the set of all possible assignments of variables x1, x2, x3 which give you the optimal value of z is not a point, not just one solution, a whole line segment. Yes.
In the very first step, how did you decide that the first row or the first column is the basic column?
So I had a tie here on the largest coefficient, 3 and 3. So I wanted to choose one of those. Well, then I tried to argue which one will increase further. It turned out that both give me a tie. Each one of these will increase only up to 2. So I just chose randomly the first one.
Okay, and what about the second?
Okay, here the pivot column was determined by the largest coefficient. So 6 is basically the only positive coefficient in the last row. It's the only variable which I can increase, which will increase z. So here it was not a choice, it was determined for me.
So in the first step, if they both had the coefficient 3 in the last row, right? But what if it wasn't 2 over 1 for both of them? What if it was?
So then I would try to take the one which can be increased further, because this will give me a bigger increase in z. I mean, it's not that it really matters. I mean, the only difference is that, I mean, if you follow a rule which increases z a little bit faster, you'll do a little bit less iterations. If you choose, I mean, if at each step we choose the column with largest coefficient, well, we hope that eventually we'll do less iterations. An alternative rule will be look at the columns with positive coefficient and choose randomly. It's also a rule. The only difference, I mean, it will also work. It will lead you to the optimal solution eventually, just a little bit slower. Yeah.
You have to include the x5 and x6 as well in the answer? Or?
So here, the only reason I included x4, well, in fact, it's even better not to call it x4. It's better to say that it's just a parameter, say t. So if you are given a problem about x1, x2, x3, basically the answer should tell you x1 is such a thing, x2 is such a thing, x3 is such a thing. All the steps in between, the slack variables, the Tableau, well, if somebody came to you with a problem, he doesn't care about your slack variables or the Tableau or whatever. He just cares about x1, x2, x3. Okay, so let's kind of extract the lesson from this problem. Once you get to the very last iteration, where all the coefficients in the last row are negative, you can't automatically just say the non-basic variables are equal to 0, basic ones are what happens on the right. Well, it usually works, but there are some very rare situations where it doesn't. And it's exactly when one of the non-basic coefficients in the last row is equal to 0. In this case, you have to think a little bit. So you'll set the other non-basic ones to 0. This one will be a parameter, and usually some inequalities will have to be satisfied for all the numbers to be positive. So I think it's the first example that we had where the optimal solution is not unique. We have a whole segment. Okay, so maybe once again, any questions about this example?
How did you figure out again that x4 is a parameter?
X4 is parameter. Okay. So I look here, and I see, well, how can I make z equal to 6? Well, the only way is to make x3 equal to 0 and x5 equal to 0. Well, but I still have another non-basic variable. The non-basic variable is the variable which doesn't correspond to a column with all zeros and 1 at one place. So this is my non-basic variable, this is non-basic, and this is non-basic. So this variable, even though it's non-basic, well, it doesn't appear in the expression for z minus 6 with a negative sign, so it can be whatever it was. It doesn't have to be 0 for z to be equal to 6. So this means it is parameter. Like, I'm free to choose it. But then once I choose it, the basic variables, they don't really have a choice. They have to adjust. Other questions? Yeah.
If x4 was an integer not equal to 0, then would x1, x2, and x6 be just 2, 0, and 1?
Yes, so if this was, say, minus 10, then x1, x2, and x6 would be 2, 0, and 1 corresponding. Okay, so let's do one more example, and let's do an example of first let me write down the example, and it will tell you what it is an example of. So the example is maximize z, which is 3x1 plus x2, subject to x1 minus x2 small equal to minus 1, minus x1 minus x2 small equal to minus 3, 2x1 plus x2 small equal than 2.
Sorry, we have a previous problem. If we got the answers we got to the original objective function on top,
Okay, yes.
the 1/2 t will eliminate each other.
Yes.
So by that logic, it doesn't matter what t is. Well, we will like if t equals 1,000,000, we can still get z equal to 6.
Yes, but so this inequalities came from the fact that the variables have to be positive. So they come from, say, why t equal to 1,000,000 will not work, because then x1 will be 2 minus 500,000, it will be negative. But I want it positive value of x1. So maybe it's actually a good idea to see what happens to the constraints and why they are satisfied under this assumption. So the first constraint, x1 minus x2 plus x3, well, what is it? x1 plus minus x2, so it's 2 minus t. Is it smaller than 2? Answer, yes. And the reason is because t is positive. So this inequality is used to satisfy this constraint. The second constraint, x1 plus x2 plus x3, well, this plus this plus this is basically just 2. And, well, of course it is smaller or equal than 2. Finally, last one, 2x1 plus x2 plus 4x3. So 2 times this, 4 minus t, and plus this, so it's 4 minus t over 2. Is it smaller or equal than 5? Once again, yes. The reason is t is positive. So this is smaller or equal than 4. So the last constraint is really, really far from being sharp. I mean, this is at least sharp when t is equal to 0, but this one is never sharp. And finally z, Well, we expect it to be 6, but indeed it is 3x1 plus 3x2 plus x3. So it is 6. So we used this inequality to make x1 positive, this inequality to make this constraint true. And indeed, it might be a good idea once you get the solution. I mean, it's kind of awkward strategy. If you have an exam and you have lots of time, it's a good idea once you get the solution, plug it back into the original function and see whether constraints are verified and the value of z is what you thought it is. I mean, that's not a guarantee that your solution is optimal, but at least it's a guarantee that your solution is feasible. Later we'll have also a way to check that the solution is optimal, kind of without solving the problem completely. But we'll talk about it in a week. So if you don't have too much time, then maybe it's better not to disappoint yourself if something is wrong, just leave it as it is. Okay, but back to this problem. I'm trying to maximize such a function subject to these constraints. Well, so what's wrong? Well, why can I start the simplex algorithm right away? Well, usually I start with the solution 0, 0. Here, well, I don't see a solution 0, 0. Well, first of all, 0, 0 doesn't work, and also I don't readily see any solution. So we'll do the trick of using the two-phase simplex algorithm. We'll relax each one of these constraints and then apply the simplex algorithm. So phase 1 of the simplex algorithm. I will try to relax this constraint. How? Well, I'll subtract a variable x3 from each one of the left sides. Once x3 is big enough, the left sides will become quite negative. Of course, they will be smaller than whatever you put here. So phase 1, I will change these coefficients to such coefficients. 1, minus 1, minus 1, minus 1, minus 1, minus 1, 2, 1, minus 1. So I added the column of minus 1s because I wanted to subtract x3 from each one of these equations. Once again, the rationale, once x3 is large enough, the left-hand side will be automatically very, very negative, smaller than minus 1, minus 3, 2. Yes.
How did you know that you have to use the two-phase?
So I looked at these constraints and I see when I try 0, 0, the first constraint is violated. So 0, 0 is not a feasible solution. And I look at this and, well, I don't really see a feasible solution. I don't know where to start. Okay, so this will be my new matrix of coefficients. And I want this to be smaller or equal than minus 1, minus 3, and 2 correspondingly. And I will introduce the stack variables, x4, x5, x6, like this. I'll join the identity matrix on the right. And finally, what function will I try to maximize? So try to remember what we do in the two-phase simplex algorithm. We are trying to relax the constraints in such a way that they will have a solution, but we try to relax them by as small amount as possible. If we succeed in relaxing them by just 0, then we are done. So what we are trying to maximize? Yes, we are trying to minimize x3, minimize the amount that we subtracted from here, which is the same as trying to maximize minus x3. So here I'll add -1 into the objective function. Well, let me not call it z because z is already taken. Let me call it double. So this problem is not the original one. It is an auxiliary problem. I relaxed all the inequalities by mark x3, and I'm trying to minimize x3, which is the same as maximizing minus x3. Okay. So that's the problem that I'm trying to solve. Next, I'll try to do some iteration of the simplex algorithm. So let me try to apply a wrong logic to this. I see that all the coefficients in the last column, in the last row are negative, therefore I have the optimum right now. Is it true? So several people say that it's not true. Why is it not true? Yeah.
Because constraints are not satisfied, for example,
Yes.
first.
So if I try, I mean, it looks like I could set W equal to 0 by just saying, well, x3 equal to 0 and everything else will adjust accordingly. Unfortunately, it's not true. If I set all these non-basic variables to 0, my constraints are not satisfied. My solution, my first attempt of 0, 0, 0 is infeasible. So yes, this coefficient is negative, but unfortunately, this whole dictionary, this whole Tableau is not feasible. These numbers on the right are not positive. Okay, so my first iteration will not try to increase W at all. That's not what I will try to do. All I'll try to do is just make my first solution feasible. So I'll try to make these coefficients positive. How will I do this? So, which variable I will try to increase to make my solution feasible? Well, luckily for us, we don't have to think. We don't have to look at this whole table. It is x3. It is always the variable which corresponds to the amount by which we relax the constraints. Basically, if we are trying to make these constraints satisfied, we'll relax them by a big enough amount. So we'll increase x3, amount by which we relax each of these constraints, from 0 to just enough for each one of these constraints to be satisfied. So x3 will become basic. If you wish, you can say that this column will be my pivot row column, but once again, not because of this coefficient, just because, well, that's the number which we can try to increase to make this whole thing feasible. That's the amount by which we relax the constraints, the original constraints. Okay, how much should we increase it? So we do want to increase it, but we do not want to increase it to, I don't know, 1 billion. That will be too much. We want to increase it just enough to make all these coefficients positive. Or just enough to make these constraints actually hold. So these constraints will actually hold. So first constraint tells me we should increase x3 at least up to 1. Second constraint tells me you should increase x3 up to 3. And last constraint tells me we should increase x3 up to whatever you want. If it is positive, it's okay. because once again, x1, x2 will be non-basic variables, will be still at 0, x3 will be some number, and I'll have to increase it all the way up to 3. So I see that this row tells me, well, gives me the inequality which is the strictest. Increase x3 at least up to 3. So I'll try to make this row my pivot row, this variable my new basic variable. So let's see how it goes. I'll try to make this coefficient 1 and all the other ones 0. Okay, so I'll take the first row and I'll subtract the second one. So 2, 0, 0, 1, minus 1, 0, minus 1, minus 3, 2. Okay, this 2 is a good sign. It is positive, so at least our solution will be feasible according to this row. Second one, I'll try to make this coefficient equal to 1. How? Well, just multiply everything by minus 1. 1, 1, 1, 0, minus 1, 0, 3. Once again, this positive number 3 is a good thing. Okay, last one. I'll add 2 times the second row. So it is 0, minus 1, minus 3, 0, 2, 1. Oh, wait a minute. Sorry. I want to make this coefficient to 0, so I'll just subtract the second row. So it is 3, 2, 0, 0, minus 1, 1, 2, minus 3, 5. And what happens to the last row? Well, I'll want to make this coefficient 0, so I'll subtract the second row. 1, 1, minus 1, 0, 0, minus 1, 0, w plus 3. So not only did I not increase w, well, I decreased it. It's now minus 3. When the non-basic variables are equal to 0, w is minus 3. But at least I have a feasible solution with what variables are now x3, x4. Yes. So the basic variables are now these ones. x3, a column of zeros and 1 here, x4, 1 here and column of zeros, and x6, zeros and 1. So if my x4 is equal to 2, x3 is equal to 3, and x6 is equal to 5, I get some feasible solution. Is it optimal? Well, no. I look at the last row, I see I still have positive coefficients. So I can try to increase one of those. Let's see which one. I mean, once again, we could just decide to increase the first one, or could decide to increase the second one, or we can try to plan a little bit ahead and see how much will each one increase. So if I try to increase x1, it will increase up to 2 over 2, 1, 3 over 1, 3, 5 over 3, 5/3. So x1, if I try to increase it, it will increase up to 1. If I try to increase x2, it will increase by whatever amount, by 3 and by 5 over 2. So which one is better? x2, yes. So once again, if I try to increase x1, it will increase only by 1 from this row. If I try to increase x2, it will increase all the way up to 5 halves, which is better. So I'll choose this as my pivot column, and I already said in the pivot row, the one imposing the strictest inequality is this one. Okay, let's do the actual pivot. I'll try to make this 0, 0, 1, 0. The first one is already 0, so I'll keep it in the go to the right. Okay, so first row, I leave it as it is. 1, 0, 2. Second row, well, I want this to be 0. So I have to subtract 1/2 times the third row. So 1 minus 3/2 minus 1/2, 0, 1, 0, minus 1 minus 3/2 times minus 1, minus 1/2, 1, 5 minus 3/2 times 5 minus 9/2. It's 1/2. I'll try to make this coefficient 1. So all I have to do is just divide this by 2. This is maybe the easiest one. 0, 0, minus 1/2, 1/2, 5/2. And what happens to W? Well, I'll try to make this equal to 0. I'll subtract once again 1/2 of this row. So this will be 0, 1 minus 3/2 minus 1/2, 0, 0, minus 1 minus 1/2, so it's 1. Oh, wait. What is it? I want to subtract 1/2 of this row. Okay. So here it is minus 1, minus, okay, so this is minus 1/2. And this is minus 1/2. Okay, I think this is correct. Let me check. So now my basic variables are x2, x3, x4. So this corresponds to the basic variables. Can I increase W any further? So W is now what? What is that? Negative half, yes. Can I increase it any further? No. So these coefficients now come with negative signs. If I try to change any one of those, well, W will only decrease. So optimum is W is minus 1/2. Okay, this optimum occurs, I mean, if you wish, when x1 is equal to 0, x2 is equal to 5/2, x3 is equal to 1/2, x4 is equal to 2, x5, x6 is equal to 0. But that's not important, because we are trying to solve the auxiliary problem, and its optimum is minus 1/2. What does it tell you about the original problem? Second. It's infeasible, yes. So the fact that the best thing we can do here is minus 1/2 tells you in the original problem to find at least one solution, you have to relax each one of these inequalities at least by 1/2. Otherwise, well, it has no solutions. So this thing being negative, not being 0, tells you your original problem is not feasible. So since W is strictly smaller than 0, the original problem is infeasible. Okay, so we solved the original problem, it just happens not to have any solutions. Okay, so maybe any questions about this? Okay, so basically in So basically now we know more or less everything there is to know about the simplex algorithm. I mean, up to a point, of course. We know how to perform it when there is an obvious feasible solution to origin. We know how to perform it when there isn't a feasible obvious solution to two-phase simplex algorithm. We know that we might encounter degenerate iterations, and it's not something to worry about. We know that, I mean, in theory, we might encounter cycling, but as long as we stick to the smallest subscript rule, we won't encounter cycling. And, well, we know when it stops, we know that it always stops. Once you don't encounter cycling, it always finds the optimum solution. It might find not one optimum solution, but several of those. Maybe just a comment about how fast is the simplex algorithm. Typically it is pretty fast, but in theory it would be very slow. So there is a discrepancy between the practice and theory here. So how fast is the simplex algorithm? Formulate the question more precisely, how fast is it on problem with m equations, m constraints, m variables. So there are several answers to this question. Typical problem usually requires, so I'll just tell the answers, I will not explain them in any way. It's not, first of all, it's not obvious what a typical problem is. So we can make it precise by saying it's kind of a problem drawn from some kind of distribution of problems randomly, and the distribution has to be nice enough, no discrete masses, something like this. But anyway, for a typical problem, you have something like, let me say some number times m times logarithm of n iterations. So it will increase the number of iterations will increase quite fast with the number of equations. It will increase very slowly with additional variables. So, I mean, you introduce the step variables, well, it's not that big of a deal. I mean, yes, you increase the number of variables, but it's okay. Lots of equations typically is harder to solve than a few equations, but still it is very reasonable thing. I mean, each iteration, well, see, it's basically, well, you are choosing the pivot row, pivot column, and doing some Gaussian elimination, so you can count that it's, well, what? So basically the hardest part is doing the actual update of the table once you decide the pivot row and column, and for this you have to do iterations for each entry of the table, something like n times n iterations. So you see that each iteration is, well, some reasonably fast, and there are that many iterations. Unfortunately, there are problems. Oh, and this constant, well, it depends on which kind of pivoting rule you use. I mean, for our pivoting rule of largest coefficients, it's one thing, maybe something like 5. For other rules, it might be somewhat smaller, but there are kind of advantages and disadvantages to using different pivoting rules in this context. I mean, our rule is good because it's very fast, in the sense that you just look at the largest coefficient and you know your pivot column. Basically, you have just to do what? N lookups. So it's very fast. Other rules, maybe there is a rule which tells you look at all possible coefficients which are positive and see how increasing this particular coefficient will affect the objective function, and choose the one which makes it the largest. So such a rule requires not just to look at these entries, but also perform some computations, and it's slower, but it will lead to less iterations, but each iteration will take a little bit longer. So, I mean, people actually do work on optimizing the simplex algorithm. Simplex algorithm is, as I said, very, very practical. People do need to solve kind of systems with hundreds of constraints, even thousands of constraints. Kind of if you make a schedule for airport, well, you have lots and lots of constraints. So it's not untypical to have thousands or huge amount of constraints. So it is important to optimize the simplex algorithm. Well, from theoretical viewpoint, this is not even close to the actual answer. There are problems taking something like 2 to the power n iterations. So not just it grows like a logarithm with the number of variables, it grows exponentially fast. So if you try to come up with really, really hard problem, well, you will succeed. And, well, I guess this holds for, I mean, this result 2 to the power n holds for the pivoting, largest coefficient pivoting rule. I think that as far as we know, for any pivoting rule that we were able to come up with, there was an example with exponential number of iterations. So from kind of worst case scenario, the simplex algorithm is not really that satisfactory. It could be extremely slow. On practical problems, it is very, very fast. So from theoretical viewpoint, it is still an open and interesting question whether you can find, say, a pivoting rule which will guarantee that the number of iterations is polynomial, kind of m to some power times n to some power. Well, nobody knows. Okay, and finally, next time we'll start completely different, well, not completely different topic, but still topic with, we'll talk about kind of shadow prices, pricing, quality, so it will be see you next time.
I was
I have great lots of I kind of figured it out, sort of.
Well, it's so good when, like, you often really actively work on it, but then you get some idea, and you're like, oh, I think I
I
can do
know, but yeah, these questions are like that. Sometimes it just comes out sudden. And then sometimes you think about it like that. Yeah, I think for
Yeah, okay, I worked on it a lot. And I just took this last but I worked on it like a week ago for like 4 hours. And then I did a little bit over the weekend, but not really.
Yeah.
But then on Tuesday, when it was due, I started at it again, and it's like, oh, I figured it all out. It was good.
but like, it's not something that's before you get
Oh, yeah, it's significantly harder. Yeah. Kind of a little bit of a wake up. But like, I assumed like, oh, I'd go. Oh, yeah, no, another thing.